thanks to the organizers. Yeah, so...
Did they talk to you about recording? Is this recording?
Yeah,
it's good. It's good. It's good. Fine.
Okay.
Fine.
Yeah, so for those who don't know, condensed mathematics is this a fairly new theory which provides sort of a better framework to study the interplay between algebra and topology or geometry by replacing the topological spaces by something called condensed sets. And they form a much nicer category, is the point. Almost form topos, and the abelian group version forms an abelian category as opposed to topological abelian groups. And yeah, so it generalizes like most reasonable topological spaces in this way. And if you're familiar with formalization, you've heard of this before in the context of the liquid tensor experiment, which was this challenge proposed by Peter Schulze a couple of years ago to formalize a very hard theorem in this theory, which he was sort of uncertain of the proof himself, and the Lean community managed to formalize this proof. It was completed, I think, 2 years ago. But this had like one clear goal to prove a hard theorem, and the contributors were really focused on that and doing everything in the fastest way possible to get there, I guess. But that's sort of orthogonal to the philosophy of Mathlib, where you want to do everything as generally as possible, and so it might possibly be used elsewhere in the library. And the goal of my talk is to give a presentation of how we've gotten the basics of this theory into Mathlib, and as you'll see, it's mostly been formalizing some very general category theory to be able to define everything. So if you're scared of condensed mathematics, then but familiar with category, then you're going to be fine, I think. And it seems like most people here are quite comfortable with category theory. So if you're bored during my talk, you can start by going to my GitHub and forking my project. There's the address, if you want to write it down. And then you can go into this folder here, and there's a folder called projects. And there's a bunch of stories there that you can work on, especially in this file. And this has really nothing to do with condensed mathematics, more like abelian categories and short exact sequences. Okay, so let me briefly explain what a condensed set is. It's a sheaf for a Grothendieck topology called the coherent topology on the category of compact Hausdorff spaces. But it has a much more sort of concrete description, or the sheaf condition. You take a free sheaf in this category, which preserves finite products and satisfies this equalizer condition that every surjective map is mapped to an equalizer diagram. And you can, so preserves finite products, you can think of this as, because it's a contravariant function. It takes coproducts, finite coproducts, and there's a map to the product, and the condition is that this is an isomorphism. And then this equalizer condition. And yeah, so this is not really that complicated. It's small amount of data. And we get an obvious functor from topological spaces to condensed sets, whose sort of S-valued points on a compact Hausdorff space S is just the continuous maps into the topological space. And this functor is faithful, so that you have to restrict it to a certain class of nice topological spaces to get full faithfulness. This property we haven't formalized yet. We just have the functor, not the fact that it's faithful. Yeah.
And what can you tell me about the compact Hausdorff space by themselves?
Sorry?
Do we have properties of the compact Hausdorff spaces by themselves before taking the sheaf?
Yeah, I mean, I'm not sure I understand the question. We have the category of compact Hausdorff spaces in Mathlib, if that's what you're asking.
Yeah.
Can you tell when a condensed set has come from a compact Hausdorff space?
Yes. You can. We haven't formalized this result yet, but it's a condition on sheaves or objects of topos, I guess, called being quasi-separated, quasi-compact.
QCQS.
QCQS. And those correspond exactly to the compact Hausdorff spaces in condensed. Yeah. So
you're saying those are the representables, or what?
Sorry?
Surely not every sheaf is a space, is it?
No.
Right. So you're saying those are the ones that are arising this way as the mirror of space?
The QCQS condensed sets correspond to compact Hausdorff spaces. So yeah, representables.
QCQ what?
Quasi-compact, quasi-separated. It's a form of condition.
Those are the spaces X, for which this is a sheaf.
If it's a compact Hausdorff,
this here is always a sheaf.
So what are you saying?
yeah, but a representable, X representable doesn't mean there's a topological space, right? It means there's a compact Hausdorff space. Because X is a functor on compact Hausdorff spaces.
Yeah.
So the claim is that the representable functors are precisely the QCQS sheaves.
Those are the compact Hausdorff spaces.
Yeah.
Right, but representable for a functor on compact Hausdorff spaces means there's a compact Hausdorff space.
Representable in this sense, like X there.
Yeah.
X doesn't have to compact Hausdorff.
That's a different question.
But that's
But it's the ones of this form that come from compact Hausdorff spaces.
Those are representable. You're telling us something else. Quasi-compact, quasi-something.
But this map isn't good. This map from top is not like, I mean, whatever the category rejective is, right? It's
Good on
not.
the good on the quasi-compact. It's those spaces.
Sorry, you were talking at the same time, right?
I'll stop.
I'll stop talking to you.
All right. So anyway, we can. There are equivalent. There are other defining sites which give equivalent categories of sheaves. So we can. A condensed set is determined by its values on actually Estonian spaces, which are the extremely disconnected compact Hausdorff spaces. It's not that important what this condition means, but it's the projective objects in compact Hausdorff spaces. And Klaus and Schultz actually take profinite sets to be the defining site, and those are the totally disconnected ones. So on the side of profinite spaces, the sheaf condition has the exact same description. On the other category, Estonian, it's only this condition here, finite product preserved. So this equivalence is not at all obvious, but it holds quite generally in our categorical setups. Now, okay, Okay, so how to set this up in Mathlib? We want to define something called the coherent topology, and it's on compact Hausdorff spaces. It's just the covering families are just jointly surjective maps, jointly surjective families. So a cover of S is a family like this, such that like everything here is hit by some map. So like the induced map from the disjoint union is surjective. On a completely general category, we can define this condition called pre-coherent, which is just the minimal condition to define this topology. And so, instead of talking about jointly surjective maps, the sort of correct categorification of this is the notion of what we call an effective epifamily. And this requires no existence of any coproducts or pullbacks or anything. It's just a condition on a family like this. Essentially, that it is somehow a joint multi-co-equalizer of any two maps that it co-equalizes.
Is this a Mathlib, isn't it? Or did this already exist?
Yeah, I think effective epifamily is sort of a Mathlibism. The notion of an effective epimorphism is not. But usually when people say effective epimorphism, they require the existence of the pullback of there, but we don't. And I mean, that notion also existed, but I think it was called, I think it's usually called strict epimorphism. But like there's this notion of strict, regular, and effective epimorphism that are all the same thing when your category has the sufficient conditions. So why not call them all effective, right? That's what we do in Mathlib.
Do we have multi-co-equalizers or
Sorry?
something? Well, you're defining this in terms of some kind of like family version, a family index version of the co-equalizer.
Yeah.
Do we have that? Like,
it's not formulated in terms of something being a co-limit, but it's basically that. Yeah, so I'll show you the definition of an effective epifamily later. And so this condition basically says that, like, when you have an effective epifamily, like this, and any map like this, it can be sort of pulled back to another effective epifamily such that everything commutes in the right way.
But there's no claim that it's a universal thing or a pullback, is that the idea?
No. Just that existence, no uniqueness or anything. And this is like the most important property of a Grothendieck topology is that your sort of covers can be pulled back among maps.
But when you pull them back, you get a canonical. Right, somehow.
What?
If I've got an open cover and a continuous map, then I can just literally pull back the open sets and I can get a canonical open cover of the...
You're thinking of a topological space?
Yeah.
Yeah, but I mean, there's only one map between any two objects. So yeah, I mean, but there's we're covering sieves. You have the pullback sieve.
And this is just something randomly exists that makes it that.
Yeah, and then you can define what we call a coverage, and this sort of generates a Grothendieck topology, and the sheaves are the same.
So this is like sub-basis and basis. It's analogous to basis and sub-basis in topology, I guess. Like.
You mean the coverage Grothendieck topology? Yeah, I guess. Yeah.
And is Y and B on your blackboard B2 and B1 on the map F?
Oh yeah.
Okay.
Right. So this is B1.
This is B2.
this family is X1,
X1i,
and this is
X2i.
X2.
What's the I function?
Is there an I and a J? In the indices can be
The
different.
indices are different, yeah.
Yeah.
So like you pull back a regular equalizer and you get like a 5 equalizer, like how's
Yeah,
that
no,
work?
there's a map of the J's to the I's, which tell you which one to go to.
Yeah. They both have to be finite in this case. Like we want finite effective epifamilies to be covers. Okay, so this property is sort of implied by two other a bit simpler properties, which hold in the case of compact Hausdorff spaces, which is the reason for this this sheaf condition being, you know, this and the other condition with just one surjection. These are a bit simpler, so the category is pre-regular if effective epimorphisms can be pulled back, and then it's just and I'm just talking about a single map. Yeah, so now it's X and Y. So this is an effective epi and it can be pulled back to a W. So this exists. And finitary extensive basically says that co-products behave like disjoint unions with respect to pullbacks. And this finitary extensive property, this is like the notion in Mathlib corresponds exactly to the one in the literature, except maybe that the literature assumes too many pullbacks sometimes. We only assume the pullbacks that appear in the definition, but like all the proofs in the literature work correctly. But this pre-coherent and pre-regular are Mathlibisms for sure. We don't even have the notions of coherent and regular, which are sort of well studied, but they're that plus the existence of some limits. Oh. Okay, so yeah, we've developed a fair amount of API for these categories and their cloning topologies and sheaves, and yeah, we're almost finished with a paper describing all of these results in the proper generality, which didn't appear in the literature.
Just out of interest, is there lots of leak code in that paper, or is it a maths paper?
There's lots of lean code, yeah. I think there are definitely some results that are never written anywhere else in the literature in the generality, particularly about the sheaf conditions and so on. But
this was something that you actually needed to make the condensed stuff.
Yeah, the thing is that this category is Estonian of extremely disconnected compact Hausdorff spaces. It barely has any limits.
Does it not have products?
It doesn't even have binary
It doesn't have
products.
binary products.
It has like, so the condition is that it has to have pullbacks on the form like, if this is like the inclusion into the co-product.
And it has co-products, is it?
It has finite co-products. It has all co-products actually, but like they're not, the infinite ones are not the disjoint union, of course.
You disjoint union, then you compact it.
It's the stone check compact.
Yeah.
Yeah, so it needs to have pullback of this shape basically, and this is yeah, so absolutely not many pullbacks.
I think it's like a problem if it has pullbacks along inclusions.
Oh, this specific category.
This category. Nobody knows it doesn't work out.
But the point is, you don't need that.
No, you don't need it, but if you want to use it, you don't.
That, you mean that, it has pullbacks along like
Pullback
any monomorphism?
Is an inclusion that is not closed.
Yeah, I think that's not. I mean, I don't know the answer to that.
Exactly.
And
and Scholz also don't know.
sorry.
Yeah, so do you mean that in the papers by Clausen and Scholz, when they say, oh, let's do sheaves on this Estonian space, it's actually there was no definition of sheaf that
Yeah, yeah,
on the
there-
literature that would apply to this category?
Yeah, there is.
There is a definition.
There is I mean, the definition of sheaf that's in Mathlib is the correct one, which doesn't assume any pullbacks. And that's also in SGA. So, I mean...
Okay.
So that was-
I mean,
it was in
this is-
SGA.
that's well known. But like, I mean more specific results about sheaves on, for the regular topology or coherent topology on a very general category. That's sort of the new results in our paper. Okay, so let's just look at.
I mean, you can define the notion of sheaf in the category of pre-sheaves. You don't need to define it in terms of the site. It's a convenience to be able to unwind it in
Yeah.
elementary terms. But you have a category.
Yeah.
It doesn't matter if it has any co-limits at all. You take pre-sheaves, and then in the topos of pre-sheaves, the definition of a sheaf is fixed once you have the topology. So,
You obviously need the topology.
yeah, but it's a question of kind of compiling it down to elementary statements about some maps in
Yeah.
the index category. It's not a question about whether something is well defined. I mean, the notion of sheaf is defined once you have the
Yeah,
topology in the category.
for sure. But I mean, it's.
But maybe you want to have a statement.
I definitely want to be able to argue on the side somehow. You know.
So in Mathlib, you want to be able to write it down into some convenient form.
Yeah.
Would it be helpful to look at the definition, the Mathlib definition of sheaf?
Yeah, sure. So I was going to show you here. Here is the definition of a condensed object in a category C. So it's a sheaf for the coherent topology on compounds in C. Okay, you want to see the definition of a sheaf?
We already covered that.
So it's, you know, you check the sheaf condition in a category by composing with the co-united functor into sets. And check that it's a sheaf for every pre-sheaf.
Yeah. That's math.
This just means that for every family of elements that is compatible, there is a unique amalgamation. You can state this completely without assuming any products or pullbacks or anything. But that's not, that's not the point here, I guess. So I was going to show you the definition of the coherent topology. If we have this condition pre-coherent that I showed you, this allows us to define something called the coherent coverage, whose covering pre-sheaves, which just means you know, sets of morphisms with a fixed target, are the finite effective epimorphic families. And then we take the generated, the Grothendieck topology it generates with this, which is just the smallest Grothendieck topology that contains it somehow. Yeah, so this is what an effective epifamily is. This is basically stating a co-limit condition without mentioning the word co-limit. So yeah, maybe let's not go into too much detail on that.
Wait, so what does it mean when you state this thing without having a co-limit? Like, does that mean that these are for all statements that have no inhabitants, or like, does it matter whether you use for all or exists here? If there's no co-limit, then is it trivially true or trivially false?
So I think if you have co-limit in your category, this data is equivalent to data of co-limit. It becomes easier.
Desk is data, right?
Yeah.
This is
Fac and unique axioms. Desk is data.
Yeah,
It's not a vacuous statement about co-limits. It's an alternative way of formulating something without assuming co-limits. So you don't assume that you have co-limits, and so you unpack it in terms of the diagrams.
I mean, I guess you could probably, we have that, I think. You could say that some cone is a co-limit co-cone, which is also, you know, that doesn't assume the existence of any colimits, right? I mean, yeah. And so, yeah, let's go back to the condensed folder. I'm going to show you the. So we have this equivalence I was talking about, and with very general like target category, you basically just have to be able to take a right Kahn extension. That's this condition that it has limits of some shape. And then it just follows from a general equivalence we proved for coherent topologies. So if you have some functor satisfying some properties such that the coherent topology is preserved somehow, then the sheaf categories are equivalent.
But this is original work, right? You're not copying this out of the literature.
Sorry?
You're not copying this out of the literature, you're trying to make sense of the literature.
Yeah, like originally we did it for Estonian compounds and Estonian and profinite and compounds.
Yeah, that's what we were doing in
Copenhagen.
Copenhagen, right? That was the strategy there.
And then we started writing this paper, and Adam noticed that, you know, why don't we formulate this property for just general categories? And it was pretty easy to just copy the code. So I mean, yeah, it's like I'm pretending that we did everything in the correct generality to begin with, but actually you do things in an ad hoc way, and you find more generalizations. Yeah.
What are all these adjectives? Preserves, reflective.
Preserves effective FPs, reflects effective FPs, that's obvious, right? That it maps effective FPs to FPs, and if the map isn't, if the image is an effective FP, then the pre-image is.
Is this the same effective FP as, like you said, effective FP family before? Is that the same thing?
Yeah, for a single morphism. Yeah. So and this effectively enough is the key property. We also invented this. It's just that it is the fact that compounds has enough projectives in the form of Estonian spaces with like surjective maps down to them. You take the discrete corresponding discrete set and then stone check compactify, and then you get a surjective map. But in a general sense,
it literally is enough projectives.
No, it actually has nothing to do with projectives. It is a statement about this functor saying that, you know, for you have f from C to D. For every x here, there is a y in C and an effective epi from f of y to x.
So that's the definition of effectively enough.
Yeah. I mean, in the case of compounds in Estonian, this is just the fact that there are enough projectives in compounds.
Because Estonian is defined to be a projective object in compounds or something.
It's not defined to be, but it is.
This is the same.
It's the same thing. Okay, so then we have this explicit sheaf condition. So here's the most general thing. Like here I have a completely general target category, and the pre-sheaf from compounds to it is gives a condensed object if it preserves finite products and satisfies what we call the equalizer condition, which is just it takes an effective epi and its kernel pair to an equalizer diagram. And I mean, this is without assuming any existence of limits on A, which is, you know, kind of silly because it will have finite products because it has a functor from compounds which preserves finite products. But you can state it in complete generality. And this here is also just formulated in terms of some limit cones. Yeah, and this also comes from the very general facts about pre-regular finitary extensive categories, which are automatically pre-coherent. And actually, because Emily was talking about the lack of examples or counterexamples in category theory in Mathlib yesterday. So I don't know of an example of a pre-coherent category which is not pre-regular and finitary extensive. So it is true that pre-regular and finitary extensive implies pre-coherent, and a pre-coherent category with finite coproducts is pre-regular. But I don't know if there's a counterexample.
Is there likely to be a finite counterexample?
There might be, yeah.
Literally finitely many objects and finitely many more.
Yeah, so I guess this is a challenge. Also, a related one: is there a family of morphisms such that the induced morphism from the coproduct, here I'm assuming the coproduct exists, is effective FE, but
This is not an effective FE family.
but the family, yeah, is not. I mean, this is just silly. But
So once you embed sufficiently many definitions in category theory, you come up with all kinds of complicated.
I'm wondering if actually this is all, if we're talking about something that doesn't exist in the correct generality. I mean, it exists, but like
The fear of God or not.
if it's too general in some sense, so that we might as well have assumed finitary extensive and pre-regular from the beginning.
And then we laugh at people doing geometric group theory when they just pile up definitions to create new paper opportunities.
This is a question about whether the definition that you've given of effective epimorphic family agrees with the usual definition of effective epimorphism, assuming you have finite coproducts.
So.
Is that what the question is?
Yeah, I guess so, but I know that it holds in an extensive category, then it's equivalent.
Yes. Well, it is.
It is because Mathlib says so.
Effective epimorphic family in the conventional way, which is this, then it's trivially true, but I don't know, because I can't read the code that fast.
Yeah.
I don't know what the actual definition is.
Could you show the definition
Of
of
an
effective?
effective epifamily, yeah, sure.
Or is it about the behavior of the coproducts in the category? Is that what's going on? Is the question about whether you've got the definition in the conventional way, or is it a question about whether the coproducts in the category behave in the correct way?
So the thing is that effective epifamilies are defined without assuming any coproducts.
Yeah, right.
And I know that if I have coproducts which behave pretty well,
In the expected way, yeah.
then this is equivalent.
Right.
But I don't know of a counterexample.
Yeah.
Of, so it's, yeah, you're right. It's a question of the behavior of the coproducts. Yeah. So I guess find a category with coproducts that are sufficiently badly behaved for this to break.
Yeah, and maybe it's because the category is some sort of incompletion, and then just co-products are weird.
Might be.
Wait, so if you if
So we
the
can
index set is a singleton, is this the same as effective FE?
Yeah. That's true. So the definition is that so it's a family of morphisms, fixed target, such that for all maps from the same target, and I have maps like this for all for all W and all Z, just, yeah, for all W together with a family of maps EI, which co-equalize every pair of morphisms like this that the original family co-equalizes. There exists a unique map like this. That's the definition.
So that's homework.
Hmm?
Homework.
Homework, yeah. Come up with these weird counterexamples.
So you can construct that, given a co-product, you can construct this map also, but it's not unique, or what?
Well,
I think it's saying it's an effective epimorphism in the category of pre-sheaves.
Because like if you have,
Get this diagram with the omega, up in the pre-sheaves, you can make the co-product, and it behaves well in there. Because that's the co-location. And there, the map is unaffected. In the usual sense, it's a co-equalizer that's current there.
yeah.
So I think that's what this is saying, it's unpacking that.
Oh, yeah, okay. Yeah. Yeah, I mean, yeah, this condition really looks like the sheaf condition. That's the thing. It's equivalent to somehow yeah, we can prove that the covering sieves in the coherent topology are precisely the ones that contain a finite effective empty family. And yeah, this is because it has to do with the sheaf condition. Okay, so
So do you manage to add all those definitions to Mathlib faster than the NLAD people can put them in?
I don't think I've gotten them interested.
Why are there no dog strings? What is this no-lin dog plane? You shouldn't be showing that.
Yeah, I don't know. I was gonna say, I don't know how Adam added this. I don't know how he got away with this. Like this should definitely be documented.
What are you doing here?
Yeah, but
In fact, I think they do need documentation.
Yeah.
4-line equations.
And then there's some 3-line explanation here of an effective family.
I mean, you could like copy your little diagram.
Yeah, sure. Like this diagram would be very helpful.
Exactly.
Yeah,
It's not blame not.
yeah, this is Adam's fault. Okay, so let's go back to the real world.
It's quite grumpy.
So actually, these condensed sets I've been showing you are already falling out of fashion, and this because of partly because of a problem that arises, because the defining site is a large category, and there's sort of no way around that in the way that sheafification involves computing a co-limit which is as large as your site.
So are you saying I can have a cover? I can take an arbitrary index set and just take loads of disjoint unions of copies of S, indexed by this uncountably large index. Is that an effective epimorphic family? What are you? What are you saying?
You mean related to this?
Yeah, I'm trying to understand where the big. You're saying you're taking a limit over a big set.
Yeah, to sheafify.
Yeah. So where? Give me an example of a big cover.
No, that's not the thing. It's not the covers that are big. It's the set of all covers that's big.
The set of all covers of one set.
Yeah, I mean you have every surjection to your compact Hausdorff set.
Every surjection.
So you're basically taking a co-limit over all the covers.
I see.
It's not that the covers themselves are big.
Yeah. I see. So arbitrary product of ZPs.
Yeah.
Projecting onto ZP. That's a cover.
Yeah.
And the product is over an arbitrary index set. That's the point. I see. Yeah. Okay. I believe.
Yeah. So anyway, there's no way around this, and in the original notes, this was solved by defining condensed sets as first defining kappa condensed sets for an uncountable strong limit cardinal kappa. So you take the definer pre-sheaf only on sufficiently small profinite sets. And then our condensed set is an object of a category which involves taking a co-limit over all these. I mean, it's a co-limit of categories, so a co-limit over these cardinals, and the transition maps are like, you know, functors which are given by left Kahn extension, and it's just it's not a very nice object to work with. So fortunately, there were other people who developed this theory at the same time or similar, and they use universals. And this is a solution we use in Mathlib. So then we make our sheaves take values in large sets. So it's a sheaf on the side of small compact Hausdorff spaces taking values in sets in universal.
What's the category of sets? That would be, that's type. Right? The category of sets is type, and that's type 1.
I mean, I'm of course it's U plus 1 and then compact.
Yeah, but I'm just trying to. I see. But this is this is bigger than the category of sets.
Yeah, this is a sheaf of large sets.
I see. So the category of sets is big, but the category of sheaves on that is even bigger or something.
Yeah. This works out quite well actually, but you get some annoying stuff sometimes when you say you want to talk about integers as a condensed abelian group. Then you first have to lift it to a higher universe to be able to do that, and that feels kind of silly. But
and presumably the guys were not doing it for computational purposes then, right? So I mean, why did they come up with this idea of universes? What were they thinking about?
I mean, just to make the theory make sense, so you're able to sheafify. Like, for example, you want to define a tensor product on condensed abelian groups, and this is not just taking pointwise tensor product on your object, but you have to sheafify. So it's unavoidable to sheafify.
I mean, it's literally to make sure you're not taking the set of all sets. Right? You've got to be careful. Apparently, taking the set of all sets is a bad idea.
And if we tried defining them as I mean, I could make the definition sheaf coherent topology compound 0 in type, but Mathlib just wouldn't allow me to sheafify. So, but it all goes away when you put a universe form.
You would just use some large sheaves or something like that, class size sheaves.
Yeah, that's exactly it. Yeah. So.
So which one did you actually do?
Sorry?
So which one did you actually do?
This one.
That's the Copenhagen definition, right?
And the LTE definition. Well, I mean, the LTE definition didn't have coherent topology. Yeah, so then there's a new solution by Klaus Scholze to just not talk about these condensed sets, but just really shrink your defining site to a small category of objects called light profinite sets, which I'll describe in a moment. And this is like apparently a sufficiently good theory in most cases, and you get you know, it's an actual topos, and you can sheafify in the category of sets, and but I guess the functor from topological spaces is fully faithful only on sequential topological spaces, and this is not.
What is sequential?
It's where you can detect continuity by sequences. So, like metric spaces, for example. Okay, so you can define these light profinite sets in a number of ways, and this first one is the one in Mathlib. So it's totally disconnected, second countable compact Hausdorff spaces. So you have a countable basis for it, basically. This is equivalent to being metrizable and having countably many clopens, and actually being sequential limits of finite discrete sets. So I guess the fourth point is actually the most obvious way to see that this is an essentially small category. It's just the data of a functor from n to the category of finite sets. And the category of finite sets is at least essentially small, and then you're essentially small. So this is nice. And this is in Mathlib as well now. And oh yeah, so like in this theory, the most important example of a test object is this n union infinity, the one-point compactification of n. And this is just continuous maps out of this correspond exactly to convergent sequences together with a limit. And you know, you can carry this analogy somehow into light condensed. Yeah, so I mean, I'm 15 minutes. I can maybe I'll just show you the definition. It looks exactly the same. You have to prove that light profinite is a pre-coherent category and just define the sheaves, and then we can define light condensed sets as, you see, you have the same universe level, not like in condensed, you need to have a bump here. And the light profinite sets are defined as compact Hausdorff spaces with these two additional properties. And here we prove like things like, yeah, we define this category of sequential limits, essentially, of a diagram in the category of finite sets, together with a cone on it in profinite sets, and the data of the fact that it's a limit. And this is essentially small. Yeah, so what's the plan with this? I guess some big projects would be to you know, define condensed cohomology, prove some theorems about solid condensed abelian groups or light condensed abelian groups.
Sorry,
Yeah.
you said you have some new results of things that were mentioned in the literature concerning, for example, topologies, right? Like the equivalence between a sheaf being a sheaf in this topology with this surjection being the equalizer. So, have you computed canonical topologies for some examples? Like, for example, in the example you give, like the natural numbers and like the compactification. There's a paper in Johnston computing the canonical topology for this side.
Yeah.
So have you taken a look at this?
Not. I mean, the canonical topology is a bit different.
Yeah, but I mean, it is something that we can take a look at. I am interested in that, for example. So I thought maybe you can say something about it.
I mean, we studied these topologies. Like we can describe the covering sieves exactly. For example. Is that?
Yeah, I mean,
you mean something like that, or am I misunderstanding the question?
Okay,
like describing the covering sieves. Is that?
Describing the smallest topology such that all representables are sheaves. That's the canonical.
That's the canonical topology. Yeah. So these are. I never remember if they're coarser or finer. They're subcanonical. So like. So every representables are sheaves.
Yeah, that's the key thing. Yeah. That's the thing you need.
But they're not the same as the canonical.
Exactly. So, but I mean, do you have actual like examples of or that's my question because I would like to see.
I don't have one, not on the top of my mind, but I'm sure.
In your work, like in your paper.
No.
Okay.
But maybe you can show me.
I mean, I have only this one paper by Johnston.
Yeah.
Do you know that there exists a condensed set?
Yeah, all topological spaces. I mean, if you believe.
Wait. Different topological spaces can give you the same condensed set. If you take a random set with the indiscrete topology, then that's the same as the one-point set, right? As a condensed set.
I mean,
I'm not exactly sure.
Condensed sets have points in the ordinary sense.
Right. But
Yeah,
I'm not
they
if
have
you're in
an
some
underlying
stupid
set.
non-Hausdorff situation, then you might not be able to find.
I think you were thinking, what you were thinking about is an issue with these this definition of a condensed set as an object of the co-limit,
Yeah.
then some weird topological spaces don't actually give a condensed set in that sense. But,
Oh,
but
okay.
if it's
So
a universe bump or light condensed set, then it does.
I think this is a more concrete question. Given a metric space, forget about this non-Hausdorff. Given a metric space, I can make a light condensed set. And is that functor from metric spaces to light condensed set, is it fully interfaceable?
Yeah.
Oh, really? So in particular,
that's
it's
not
injective on objects or whatever?
I mean, injective on object is an evil notion.
No, I know. But I mean, somehow. So
But
there's an
it's
example. Every
bijective on
metric
maps,
space. That's a reasonable. I don't believe your example every topological space.
But metric spaces you believe.
But metric. Well, I'm asking.
Yeah. It's,
Okay, so that's a.
it's not in Mathlib the fact that this pointer is fully faithful.
Right. But it's true.
It's true.
So there you go. So we've still got metric spaces.
Yeah.
But we've just got a bunch of other new crazies.
Yeah, and we lost general topology.
We've lost general topology.
Like
Your mind might be a step in the right direction.
I mean, for instance, you lost the pointwise convergence of functions from real numbers to real number.
Aha. Which is not
This is an example of a sequential space. So that's kind of the reason to invent general topology, is that if you don't have general topology, you cannot even say that pointwise convergence of function is a convergence in some sense. This is not metric. This is not metric precisely because it's not sequential.
Okay, so let me end by showing a few more concrete projects. So these are some, pretty hard projects that are long term, but something I'm going to be working on this week and next week, and anyone is welcome to join me, is the following 3 projects. So it's very important that the category of condensed abelian groups or light condensed abelian groups satisfies certain so-called AB axioms, which Grundig defined. And this is a condition on certain limits and co-limits to be preserving short exact sequences, basically. And I guess the most important one is AB4 star, countable AB4 star in light condensed abelian groups. So taking a countable product preserves exact sequences. And yeah, that's the AB file in the project folders if someone is looking, and that's the most developed one in some sense, but it's mostly a matter of connecting some existing API, I think, to state them and reduce it to, you always know that limits are exact on the right, for example, so it's a matter of checking that it preserves epimorphisms.
Does AB
the
stand
other
for
way.
anything?
Sorry?
Does AB stand for anything?
Abelian. There are conditions on abelian categories. So.
Can we get a language model to prove them? Because,
I mean, yeah, maybe that's a challenge to AI people. Then there's this, I mentioned this one-point compactification of N, and the free condensed abelian group on that set has this amazing property of being internally projective. So projective means that the Hom out of it preserves epimorphisms, and here you require that the internal Hom out of it preserves epimorphisms. And of course we need to define this property, which is easy, but then we need the closed symmetric monoidal structure on condensed abelian groups, and this should really be done in more generality for abelian sheaves. And then this last point is, I think, not too hard. Could be a fun project to work on. It's really just topology, I think. And then using this, we should be able to define the property of being solid in light condensed abelian groups, which is some sort of completion property. And for that, we need to define this quotient, whatever that means, and define a shift map. So this is somehow classifies null sequences, and being solid is formulated in terms of this shift map. Like 1 minus this shift map induces an isomorphism from Holmes out of or into your guy.
Sorry, when you talk about internal harms, are you talking like something relative spectrum, for example? Is the same thing, or what is it?
So internal harm means that just right adjoint to the tensor product.
Oh.
So for example, you can think about the category of abelian groups. You have an abelian group structure on the home sets, and this is this is internal in the sense that it's an object of your category, the home set. And you can prove that giving a map out of a tensor product is the same as giving a map from the first component into the home set. This is completely analogous in just a more general setting with tensor products.
But it's not true for topological spaces. This is the point.
Is this the
I
same?
mean, yeah, a simpler property is Cartesian closed, which is this mapping out of the product is the same as mapping into the mapping set somehow. And this we have for sheaf categories, that they're Cartesian closed for sheaves of sets.
So what's the difference between an internal Hom and an exponential object?
It's a tensor product.
Structures monoidal.
It's a left adjoint.
So you wanted internal humps for condensed abelian groups, or do you also have it for the lightweight ones?
I want it for both. And it should exist for like very general abelian categories with a closed monoidal structure and a reflective subcategory. Someone started working on this in Copenhagen. I think Alex and maybe you. Yes. So if you have some code that if you don't want to work on this, I would like to see your code.
I think there's some code, but
yeah, the goal was to prove this Thay's reflection theorem, right?
that's right.
Yeah. You had a question?
Yeah, I had quite a few condensed. We can think of them as some kind of spaces, but do they have any interesting cohomology, or are they more like sets? They don't really have any.
They have interesting cohomology.
They do, yeah. Because you're all set up to do that.
Yeah.
What cohomology theories exist?
Sorry?
What cohomology theories exist?
One at a time, please.
Yeah. Sheet cohomology, I mean, this is kind of
Sheet
set up.
cohomology, yeah.
You've got a sheet topos here.
Yeah.
You're kind of set up to do it. Is that where you're headed?
Yeah.
With this machinery?
Yeah, and yes, like there's some work to be done still, and this these you then need to study derived solid abelian groups, and then this cohomology comes.
So you're expecting there to be some interesting cohomology?
Yeah. There are results like relating it to sheaf cohomology and like just singular cohomology on compact Hausdorff spaces.
I was going to say, can you recover a singular cohomology?
On a compact house.
Yeah, compact house.
It's not expected to small.
We should thank our speaker and carry on.
Yeah, I'm done.
Okay.